Thank you for having me. I'm going to get started. So, I am an assistant professor at Columbia University in the Department of Biomedical Informatics. I'm affiliated with the Data Science Institute, Computer Science, and the SNF Center for Precision Psychiatry and Mental Health. Today, so the lab that I've set up, we kind of work in improving the reliability and robustness of AI models for health and medicine. The broad talk that I have made today kind of gives an overview of what's happening broadly as a landscape, and then I'll basically give one or two examples of some things that we think are quite promising. We build models in multiple application areas of health, such as psychiatry, cardiology, as well as rheumatology. And today I'll just focus on the rheumatology example, but I'll be happy to take any questions in other areas if folks have any. So just to broadly set ground, the way we could potentially think of artificial intelligence, not just in healthcare, but more broadly, is it is not new, and expert systems have been built not just for broad data, but also for health and medicine, starting from 1950s. And so the evolution of artificial intelligence has been kind of interesting because in the early 1950s, when the so-called expert systems were being built, a lot of it was around incorporating as much human knowledge as possible, relying as little on data, mostly because not a lot of data was available in the forms that we have today. So this is generally the purview of symbolic AI. Um, as we evolved through the progression of broadly general artificial intelligence as a domain, it kind of bifurcated into some statistical and probabilistic notions because over time, more and more data came to be digitized. Some of the early sort of developments in that area were late 1980s or so when the first convolutions were neural networks were invented. And the idea here is that you're getting more and more data and you're not trying to incorporate human knowledge. You're still doing it, but not as much, but you're relying on statistical patterns in the data to predict or learn something about the task that you're interested in. Over time, this kind of switched, and late 2000s was the beginning of the era of deep learning, which essentially meant more and more reliance on larger and larger scale data and even less of domain expert knowledge. The hope was that these deep learning models, you just engineer them in a way that they can extract meaningful representations for whatever task you're interested in. And now we are in the era of what we could call foundation models, where we've essentially trained models on web scale data. And most of the effort is the architectures have sort of consolidated into a specific form. And I'll go through some examples of what has been working in health and medicine. Um, but these architectures are now consolidated, and most of the effort is in the engineering and the scaling of these models. And we think that there are some more interesting reasoning capabilities at this scale. Um, Whether or not that's true is still being figured out, but that's how one would want to think about the progression of artificial intelligence broadly as well as in healthcare, because healthcare AI has followed some of these trends, though not always. The causes for these advancements had to do a lot with like availability of internet scale data. The famously known dataset ImageNet was the main one that started sort of the deep learning revolution. It was a massive dataset scraped through the web for object recognition, and essentially it contains images of about 1,000 objects with a specific semantic hierarchy in it. And around 2012, we saw models performing increasingly well with deep learning, on object recognition tasks using this kind of data. And over time, we saw eventually that these deep learning models essentially exceeded human performance. Um, that is where we started to believe that deep learning models have significant advantages over traditional ways of learning, and we started to explore basically application areas where machine learning could contribute. So the key advantage of deep learning models is in their ability to learn good representations. Everybody probably has some thoughts about this or has seen this version one way or the other, either in image recognition or in language. But if not, the idea is that these deep learning models are essentially massive nonlinear transformations, which are given a data set and a task, such as object recognition, are able to learn patterns by themselves instead of having a human provide them by hand. So as you can see in the top example, if you want to recognize the object as a bird, these deep neural networks or convolutional neural networks can essentially um, uh, increasing semantic difficulty, recognize certain aspects of the image. So the first layer will essentially recognize the edges of the bird. The second will actually go into the details and so on and so forth. This has been recreated in multiple data sets in multiple forms all the time. And it is interpretable in the sense that for natural images, at least we understand what these models might be doing. Same thing for machine translation or any kind of language-based models. You are essentially modeling them as a sequence, but the encoder decoder structures are effectively consistent. And just by forcing the models to accurately complete the next word or the next sentence in the translated language, we can just basically take massive data sets, scale it out, and the model just learns complex associations. On the right, you are seeing what parallel advances are happening within the space in healthcare. To just give a very easy, quick example, um, you might have seen massive vision language models in broad application areas. These days, you might be using it to generate some images. But in pathology and health world, some interesting things have happened using similar models. For example, if you have massive pathology data set, for example, a lot of people in community groups that are health community groups actually post their pathology images when you get a biopsy, and then you have a corresponding, say, diagnosis or you of a particular malignancy or benign malignancy, though people would want to share that in a community to understand what are the implications for them and so on and so forth. So the example that I'm giving you on the right is basically having some authors scraped all of this data and essentially created a vision language model that can look at the associated captions for any given pathology image, and tell you what potential diagnosis you might have. And this is essentially the same way web scale vision language models are trained, where you have an image from the internet, corresponding caption. You train a model so that when you give the caption, you can generate an image. This is basically the same class of models. If you give a pathology image, the model will essentially lay down hypotheses of potential malignancies or not. So these are some of the advances that you can actually see while foundation model revolution is happening beyond on web scale data. And so the democratization of internet scale data has been a big part of this. And as we know, this is not just true for something like object recognition, but it was true for massive data sets that solve different kinds of tasks. For example, machine translation, object recognition is an example I just gave, facial recognition, as well as actual generative language modeling. We've trained web scale data in the form of large language models at this point, and they seem to show some capabilities that some might call reasoning capabilities. So a big factor in being able to do this is the availability and democratization of internet scale data. Some of the other things that contributed, as you might very well know, is scalable compute. First is hardware innovations. Second is open source software. And third is basically access to this kind of infrastructure. And this has played a huge role in what we see as current foundation model revolution. On in parallel in health and medicine, these advances have also taken place in a different way. So in the past decade or maybe 15 years, many large scale databases have started to become available for research purposes. They are not publicly available because this is patient data, it's private, it's sensitive. But for researchers who want to discover biomedical knowledge, many data sets have become available. On the top right, there are examples that are entirely for research knowledge discovery purposes, such as the UK Biobank or the All of Us data. What these data sets are doing are they are massive registries where patients enroll in a study and you start taking periodic information about the patients, including their genomic data, their wearable data, their survey data, and so on and so forth. UK Biobank has about 500,000 patients. All of Us is the United States equivalent of that data set. Also includes survey data, wearable genomics, and actual clinical data. Clinical data is when you meet the doctor, the doctor collects some information about you, and then that data is basically digitized and available. And now all of these data sets have been joined together for patients who have consented this to happen and is available to researchers for research purposes. The All of Us data intends to go to capture all of this for about 1 million patients, and the efforts are still ongoing. So this is not just for scientific research. On the other hand, hospitals have managed to digitize all of the health records for patients for pretty much throughout the country in the United States. And so if you look at the major hospitals, almost all of the electronic health record data, which is essentially data that is collected when you visit your care provider, is essentially digitized and available in standardized form for research purposes. Not every hospital is going to have a research component to it. Not every hospital patient consents to doing research, but for all intents and purposes, the data is digitized. And so people who have consented for their data to be used for research will make this kind of data available in digitized form. Similarly, massive claims data sets have always been available. And now you can actually combine all of these data sets along with the fact that we have digital wearable data from your mobile health devices, genomic data. All of that can be combined to generate new insights. And that has been a big part of what is happening in healthcare. And today, that's what I'm going to be focusing on, is basically advances in health. So to ground that, where AI might be even useful in this kind of domain, which is how do we improve human health, especially using data when patients are actually sick and using the healthcare system so that we can basically improve patient outcomes. You can divide the tasks that artificial intelligence or machine learning can help accomplish into basically four aspects like being descriptive, predictive, prescriptive, and generative. These correlate well to the kinds of algorithms that are used downstream in order to achieve these tasks. So, for example, you may want to simply summarize long patient trends and patterns, and that's a descriptive model. Machine learning models and AI is very good at things like summarization. Predictive is when you want to forecast future outcomes for a given patient so that you may catch certain things early. You may be able to diagnose a certain condition early. You may be able to flag that this patient might require additional screening because they have some risky biomarkers. You may be able to be prescriptive, figure out which medications are working for which patients for a particular condition, such as type 2 diabetes, and then you can prescribe medications that actually work for specific patients. going towards not just broad swath protocols and policies, but trying to personalize things a little bit based on our understanding of the patient data. And lastly, these days, even generative models such as LLMs or vision language models have been very useful in health settings to improve clinical workflows, like automatically generating clinical notes or discharge summaries and things like that, or just summarizing um, what a patient visit would have looked like. And so, just to give you quick examples that ground this, um, one example would be of a descriptive task would be to summarize patient records over decades of their data. And this kind of a summary can actually help a doctor, a nurse, or even the hospital figure out what might be the best set of resources to allocate for particular patients. Forecasting is the patient at some sort of an adverse risk? For example, if a patient is in the ICU and nurses are worried about patients, then the way in which they write and the amount of documentation they create about the patient is quite indicative of whether the patient might deteriorate. And AI models are now being used as well as being trialed to successfully show that just learning from these patterns can actually help improve ICU outcomes for patients. And that's actually pretty interesting because you're actually using patterns that nurses already document as part of their clinical workflows in order to improve patient lives and make their experience in the ICU, which is difficult anyway, a little bit better and improve their outcomes. A prescriptive task would be, let's suppose I'm monitoring a patient in the ICU. Patients are really sick in the ICU. They have to be constantly monitored. They are given multiple interventions at a time. But given how difficult patients are to manage within the ICU, there is a lot of variability in best possible treatments and practices across healthcare institutions, as well as depending on patient type and their background. And so, what happens is we can actually take all of this data for thousands of patients and actually learn what is working and what is not working. And all of this can be done using machine learning. And then you can personalize, for example, how long should a patient be on a mechanical ventilation, which is an invasive and not a good experience for patients. So these kinds of aspects can be improved significantly by collating data from thousands of patients and learning statistical patterns. And this is achieved using something called reinforcement learning, although we are not going to go into significant details about this today. And finally, generative models are models where you can create new content, such as generating an image, generating a piece of code, generating a report, what have you. And all of these are also now being explored and evaluated in the context of clinical workflows. And so now that I've given some high level examples, it's good to categorize what kinds of tasks we might achieve using AI in health and see whether or not they actually improve things for everyone. So one category of task is automating clinical tasks. Certain tasks are clinicians are required to do as part of giving care to a patient, and they can be cumbersome, but they don't improve patient outcomes directly. For example, besides taking care of the patient, the doctor has to document everything and make sure everything is in place, not just for insurance purposes, but also so that when the patient follows up, they know exactly what information to look at and so on and so forth. Now, all of this can add significant burden to the clinician, whereas they could actually spend time treating the patient better and paying attention to the patient concerns and so on and so forth. So automating certain cumbersome clinical tasks is sort of the lowest hanging fruit of what AI can do. And this has been tried for certain things, like let's suppose there is a radiologist whose job is to look at chest radiographs and generate a report about potential pulmonary and respiratory diagnosis the patient might have. Then radiologists have to spend quite a bit of time looking at each chest radiograph, carefully assess exactly what might be happening, follow up if with any previous x-rays the patient has received, compare the two, and then create a note that can actually summarize the findings. And the note that is generated is then used by the doctor to say, okay, this patient has this particular diagnosis. Part of the process is important where we definitely need the radiologist's attention to make sure that the diagnosis is very accurate. But part of it is something that we could automate because the note itself that is generated has very specific structure. And there is no need for the radiologist to basically recreate that structure all the time. And so one of the things that could help is if we could automate the process of generating the scaffolding of the note. And then the only thing that the radiologist has to do is confirm that this corresponds to uh, their own interpretation of what's happening to the patient, verify it, and then send it out to the doctor so that the doctor can then provide an accurate diagnosis. So these kinds of tasks are more like task automation rather than using AI to discover something new. As, same thing with something like pathology. If a doctor refers you to get a biopsy, a digital pathology image is created out of that. These are massive images, they are gigapixel size, and the malignancy can be in a very tiny portion of that image. And so a pathologist's job is to carefully look at different parts of the image and then provide an interpretation of where they see there might be a malignancy, how severe it might be, and so on and so forth. And this task can actually be made easier if the risky areas of the pathology can essentially be highlighted by the AI. And so then that way, it's basically aiding their general workflow instead of creating new insights. The second kind of task is something like reflexive actions. So for certain kinds of things, for example, let's say a patient is in the emergency department and there is a particular set of exams that the nurse has ordered. Based on the outcome of the initial labs, there are certain follow-up tests that are almost always done if a patient has certain kinds of profile. Like, for example, if they have some deficiency in iron or white blood cell levels are high or something like that, some follow-up action is automatically required and it is part of the protocol to make sure that there is nothing wrong with the patient that is associated with these abnormal values. And so these are known as reflex testing. And machine learning models are great at being able to predict when a reflex test would be required of a patient. And then the human doesn't need to intervene, just make sure that the patient actually gets the reflex test and then the doctor can actually take a look at it so that nothing falls through the cracks. The other kind of clinical task could be something like automating some sort of decision support or augmenting the decision process in the first place. And this is important because there are still chronic conditions like diabetes, hypertension, where not every patient responds basically the same way to the treatment once they are diagnosed with each of these conditions. And what that means is that even though very standard medicines or something like metformin is like the first line of treatment for diabetes, not all patients respond well, and then you have to change that medication out. What we could then do is actually use all of this data of what has happened in the past and what kinds of treatments have worked for which subsets of patients, and then instead directly optimize for those treatments. And then the machine learning model can actually recommend to the doctor, look, maybe this patient may not respond well to metformin, and maybe we should give something else. What that would do is not just help give better treatments, but also reduce variability. What happens right now is that this variability makes it look like patients are not receiving consistent care. And that is something we can reduce by using machine learning models. And similar for hypertension. This is true not just for chronic condition management, but also basically integrating different sources of data because the doctor can actually look at maybe one piece of data at a time. However, the advantage of machine learning models is that we can integrate multiple sources of data, genomic data, healthcare data, digital health data, all at the same time, which could potentially generate insights, though it has to be done very carefully on how you actually do the integration uh, in order to add insights that the doctor may not already know. That is kind of decision support or augmenting clinical practice. And lastly, the most risky but also exciting is to do better knowledge discovery, to provide new clinical insights and maybe identify new screening tests, new ways of diagnosis, and new treatments that might be working. And this is true of similar examples like chronic condition management is a big part of where you can actually use data that you've already seen before of variable treatment and variable outcomes in order to generate scientific insights that people haven't seen before. And so the way to think about how this could integrate in a given hospital, think of your own massive hospital system, is what is known as a learning health system. A learning health system is one where you systematically gather data, you then basically get insights from that data, and you could use any method to generate those insights. And then whatever evidence you find of what is working and what is not, you can test it out and then put that into practice. That will help you collect new data and then improve clinical practice in that manner. And so machine learning, as you can imagine, is very integral to these aspects and in every part of it, where you can actually use machine learning to collect better data, to generate better evidence, and then to also improve practice, such as clinical decision making or automating routine operational tasks that the doctor has to do, but is just cumbersome and burdensome for them without improving patient outcomes. So that's basically what some of what my lab does. So one of the things that I'm going to skip this slide. One of the things I'm going to talk about is because we are using messy healthcare data when patients are actually sick and touching the hospital system, the data sources are not necessarily the cleanest. They can be noisy, they can have a lot of missingness. Um, Doctors may not always have time to record everything if they are busy taking care of the patient, especially in a setting like emergency care. And even if we do know what to collect, not everything is collected about a patient. We don't necessarily collect genetic data for everybody unless it is warranted because of being at risk for certain kinds of conditions, which means we have some missingness about patients, which can affect our ability to predict well. And so all of these things need to be modeled very well. Otherwise, we run into the risk of making these models unreliable and fragile when they are actually put into practice. And that is what has been somehow affecting the health and medicine world with AI until very recently. For example, the models can get confused very easily. So these are basically examples of how a model can, in fundoscopy, like basically diagnosing retinal fundus images, um, or pulmonary or respiratory conditions from chest x-rays, or melanomas from dermatology images, can get really confused by adding some very minor artifacts into the image. So as you can see, these are essentially adversarial patches that could be inserted into the image, and then the model's understanding of whether or not there is a disease in that image or a malignancy just completely changes from 0 to 100% or the other way around. So sometimes these kinds of issues can make the model basically pretty fragile and not useful for clinical practice. On top of which, the scores that come out of these models may not always be the most reliable. So, for example, Essentially, what that means is that the AI models can be confidently wrong, and this is dangerous in healthcare. If the model says the patient has zero point 0.7 risk of developing or getting diagnosed with diabetes in the next 6 months, we better be sure what that means. Unfortunately, that's not really the case with deep learning models all the time, unless they are trained in specific ways. So here is an example of where the image is that of a panda. The model has 57% confidence. If you just add a little bit of noise, nothing about the image semantically changes for the human eye, but for the model, the image now looks like that of a gibbon with 90%, over 99% confidence. And that's pretty bad if semantically nothing about the image has changed. This is kind of an analogous example to this kind of an adversarial attack to these models. Certain times, distribution shifts are the cause or even reasons why machine learning models can rely on what we call spurious correlations. So, easy example of this is, let's suppose you take chest x-rays from one hospital and you design a deep learning model to detect pneumonia from these chest x-rays. And the model seems to work very well. Now you test the model on a different hospital, you see a significant drop in the model's performance. We really aren't sure what happens, but if you look behind the scenes, what might happen is the model can pick up on associations that are present in one hospital but break down in another. And sometimes these associations can be egregious and, in fact, clinically not even meaningful. So in this example, what I'm showing you is the chest X-ray on the left. The red region is where the model is focusing on to make its prediction about the pathology. But as you can see, the model is actually fixated on the watermark in the X-ray, and in fact, not even looking at the lung area in order to make its predictions. And that means that if the data is not cleaned well, or if we are not mindful about what is the quality of the data that's going into the model, then the model can rely on these correlations to make their predictions that have no connection with the clinical or the physiological meaning of what is actually happening to the patient. And so these models have to be designed very carefully in order to make sure that that is not the case. And this has been tested in multiple settings. For example, the EPIC sepsis model is a model that was released by one of the biggest healthcare EHR company, EPIC, and was rolled out into 9 healthcare institutions to detect sepsis, which is essentially a very severe inflammation that is hospital acquired when patients are admitted into the hospital. And if not detected early, it can deteriorate very quickly and can prove fatal to the patient. And many patients can actually die because of getting sepsis within the hospital. And so detecting it early is very helpful because patients can be treated with antibiotics and the infection and inflammation can go down. This model was detecting who might end up developing sepsis, except that the model did not work very well across multiple hospitals, and in fact had significant variability across many hospitals. The particular hospitals where the model did not do well were patients where the patients were more likely to have other comorbidities like cancer. And so testing these models well is also extremely important. And so with that background, I just want to quickly emphasize where things are moving within the healthcare space at this point. So first things are, we are in the space of what are known as foundation models. And why are they interesting? Before, we used to train one machine learning model for one particular task. So for example, if we wanted to detect pulmonary and respiratory conditions from chest x-rays, we would train one deep learning model that takes x-rays and then provides us with the diagnosis. Now we have gone into what is known as the foundation model paradigm, where you pre-train models on simple tasks with large amounts of data. And these simple tasks can be really, really simple, like complete a part of an image, or if it's text data, predict the next word. And these kinds of simple tasks can be done without any labeling. and therefore you can get lots and lots of unlabeled data to use for pre-training, and then they are fine-tuned to address multiple tasks. For example, in the right, I'm showing a very silly example of next token prediction or next word prediction, where the input is 1, 2, 3, and the model's job is to predict 4, and you have a massive foundation model which then spits out the probability of what are the next possible words and shows that the highest likelihood is for the number 4. These are the probabilities it will spit out, and then that's basically how it will continue to predict the next word. And once you do that, the models have already gained a reasonable representation of what the input data looks like, which can then be trained for many different tasks. So the downstream tasks can then be what I show you on the bottom. It could be multiple choice questions, figure out the similarity between two paragraphs in a text, or complete a story, or classify a piece of text, say, into a genre. So this is where we are now. And the foundation model paradigm is also being used within the healthcare setting. And there are many good reasons to believe that this might actually change the way we do healthcare. Why? Because again, we are combining multiple sources of data like images, health record data, patient signals when they're admitted to the ICU, their omics data such as genomics data, any data that might come from their wearable devices, any notes that were taken, any surveys that were taken for the patient. We can combine all of that, not just about the specific patient, but then we can use it in the context of broad scientific literature of which treatments work for whom, what kinds of patients look similar, and generate insights that are much, much more interesting than what we could ever do before. And that is why there's a huge interest in making these models work for health data and diverse forms of health data. And so there are ways to think about large language models pretty much analogously to electronic health record data. To give a very quick example, when you visit your doctor, let's say you have a primary care doctor at a particular hospital, you get some follow-up tests, and you are living in the same city for over 10 years, that entire patient trajectory is sitting in that hospital system in the electronic health record data. And so that entire trajectory is basically like analogously like a set of sequences of events. If you look at language is basically a sequence of words. And so the same paradigm that has been used for modeling language, basically generative AI or large language models that use next token prediction, can also be used for electronic health record. It's just that we are now predicting a very complex word, and that word consists of all the conditions you were diagnosed with on any given visits, all the medications that you were given, any procedures that were done to you, and predict and when the visit even was. If all of this could be predicted very well, then this could become a very good sort of pre-training mechanism for electronic health record data. And that's exactly what we've been looking at Columbia. Some of my lab has been testing and training new models that are generative models on Columbia electronic health record data. You can see some of the tables, and other healthcare institutions like Stanford have also trained some basically foundation models on this kind of data. And the advantage of that is we can actually solve many different tasks all at once by just training these massive models. So let me give you an example. We train these massive models. You will see names like BERT, GPT, Llama, Mamba, because they are all basically next token prediction or mass language modeling, same kinds of foundation models that are used for language, except trying to predict all aspects of a patient's health record. And so we've tried this on Columbia patient population and looked at how well can we figure out whether certain kinds of patients will go on to get a diagnosis of lupus, which is a complicated autoimmune condition. that can be debilitating and has to be managed pretty well. It's The inflammation response can be pretty severe. And so what I'm showing you here is how well these models can do for something like this in comparison with models that were trained to do one thing and one thing only, which is to predict who can go on to get lupus, which is the table you're seeing on the right side. And all the numbers you're seeing in the red essentially is showing you that these models can do much better than training one model at a time for any given task. And so these foundation model paradigms are not just great for language or image generation, they are also good for health and medicine data. And we have some early evidence of that. Not just that, it's not just about lupus, but simultaneously we can predict uh, basically 14 conditions all at once. We can predict 11 of chronic and acute conditions that you can see on the left-hand side, such as who will get a heart attack or who might get diagnosed with celiac disease, who might get diagnosed with osteoporosis, who might get diagnosed with pancreatic cancer, mental health conditions like schizophrenia, type 2 diabetes, lupus. Along with that, we can also predict certain patient outcomes. For example, who might have a long length of stay in the hospital. Why is this important? Because hospitals can then designate appropriate resources to the patient who might actually have long length of stay, who might be readmitted. If somebody has a higher chance of being readmitted, then we can actually allocate resources for the admission process or figure out why the risk is so high, and we can intervene on the patient to reduce the risk of readmission. So basically, we can solve a variety of diverse tasks by just training one model as long as it's trained on large amounts of data and trained well. And I don't know how much time I have, but basically, given that this is where we are testing this for other kinds of data sets at this point as well. And this is very promising. This is happening not just for tabular health data, as I've seen now, as are shown here, but this is happening for pathology, for genetic data, and all other kinds of data sources. So it's a very important and exciting time to be able to see whether this kind of a paradigm can help improve patient outcomes significantly. And then we can also start looking at insights from different hospitals. Right now, we are still training data on one hospital, but if we can actually combine data sets from multiple hospitals while preserving patient privacy, then we would be able to provide better insights for patients and their outcomes. So with that, I'm actually going to stop because I think the talk was for 45 minutes. Um, and happy to take questions. Just to summarize what I've basically covered today, most of the advances these days are happening because of our ability to access and train on large scale health data, kind of in parallel, but not at the scale of web scale data that you're seeing as a revolution in, say, large language models or vision language models on internet scale data, but things are happening and they do have a strong potential to improve our ability to predict patient outcomes or even diagnosis. But of course, they have to be trained very carefully and they have to be tested very carefully. And that is part of what the lab does in figuring out how do we work with doctors to figure out what are good tasks, what might be helpful for patients, and then we go back and design all of these tasks. So hopefully we can actually maximize the impact that we can have on patients. And with that, I'm happy to take questions. Thank you.
Okay, thank you very much. It was very, very, very informative. So if you have any questions for Professor Joshi, please raise your hand. Yeah, Prafula. I mean, you're a co-host, Prafula. I think you can probably just unmute yourself. Yeah, you can talk, I think.
Yeah.
Prafula? Yeah.
Yes, I am. So, Dr. Joshi, it was a very, very informative talk, and there was great information. Actually, I think I improved my understanding of what is going on. But I have like A couple of questions.
Mhm.
Number one, is some to get some perspective for myself on
Mhm.
what stage is this AI research at. And let me just elaborate a little bit more.
Mhm.
That is that, for example, if you see the chest X-ray, right? And suppose you see some dot over there. And the reason why I'm saying dot, because I just saw one uh,
Mhm.
news item in, I believe, New York Times or something today.
Mhm.
There was a chest X-ray with a dot. And question is that if you show your AI model an X-ray like that,
Mhm.
is it going to give an answer saying that, look, this is possible, it is possible that this is lung cancer,
Mhm.
and I have X% confidence in my answer. Will
Mhm.
it do that?
Mhm.
Or will it say that this information is not enough for me to come up with a diagnosis,
Mhm.
but I would like results of some other test
Mhm.
in addition to this?
Yeah.
Okay, are we there yet on that it will suggest to the human being or the doctor, etc., that this is not enough, I need
Yes.
to look at it, and it will look at its data. So
Mhm.
that is one question.
Mhm.
Second question is that essentially the next test, what it does is that
Mhm.
if you look at this information theory, originated by people like Claude Shannon and all,
Mhm.
this new information will actually reduce
Mhm.
the possible outcomes
Mhm.
over which possible outcomes that can be contain, reduced. The set of outcomes can be reduced,
Mhm.
right? Okay,
Yes.
so if that can be done, is the AI in its current state
Mhm.
able to balance the information arrival of a new test
Mhm.
and the cost of that new test?
Mhm.
Can it do that trade-off?
Yeah. So to
And
your
that is
first
the third
question,
question.
uh-huh.
And the third question, actually, I don't know whether it is even fair to ask that question, but I'm going to ask anyway.
Mhm.
The diabetes example you gave, where you say that right now the first cut treatment is give metformin.
Mhm.
If metformin doesn't work for 3 months, then move to something else. And let's say your research says that for a chunk of patients, metformin is not the right
Mhm.
choice. Okay. Now the manufacturers of metformin are quite likely to fund research
Mhm.
to prove that you are wrong.
Mhm.
How do you deal with
Mhm.
such a situation in real life? So
Yeah.
those are the three questions.
Yeah. To your first question, yes, people are trying this. It is in preliminary stages, and people are exactly using concepts from information theory and cost benefit trade-off of data collection as a way to improve the potential reasoning capabilities of these models. That's happening, but there is no work that has made its way to, say, a product that is actually used in the hospital. But some of my lab is working on developing some methods, and we in our objective function we definitely use notions of cost of collecting data as well as notions of information gain as a way to do those trade-offs. And we also figure out exactly which when should the model not provide a recommendation and instead say it is too uncertain, let's defer to the human expert because the human expert may have more information in this case than what I as a model see. So these things are definitely happening. There's also testing going on about when exactly is the model better versus the human better versus the model plus human better at improving predictions. Currently, it appears in multiple cases, it appears that the model's predictions tend to be the best. The humans, despite being expert doctors, tend to be slightly worse. And the model plus AI, when when the human expert sees the model prediction and then makes their own decision actually tends to be somewhere in between the two. At least in a couple of use cases that has been happening. It is not definitive that it is always true. So I don't want to be very specific about that, but in one or two cases, we've seen evidence and papers have been published that show this.
Okay.
To the last point, I agree that this is a very valid concern, but I think that is somewhat a systemic issue where maybe it is, if you definitely have sufficient neutral funding, hopefully researchers are going to be, it's a part of research ethics to be completely neutral about these kinds of outcomes. It's not something one researcher can do or solve, but a combination of regulation and a combination of research ethics should hopefully be a good starting point to address that.
Okay. Thank you very much.
Okay, Sam, you have a question? Please go ahead.
Yes, thank you. My question is, how do you think these advancements in AI and medicine will affect how insurance companies cover or insurance companies cover treatments for patients? And do you think it is going to increase the cost of getting treatments and medication, or is AI going to decrease the cost of to the patient or to the doctor's facility in general?
Yeah. Good question. I think for that, it's so people are still figuring this out and people like regulatory bodies are trying different models, specifically reimbursement models where you may be reimbursed for particular kinds of screenings depending on the severity of the outcome. So the reimbursements are for the model to run inference on, say, ECG data to predict whether somebody will have structural heart diagnosis. And given that that may be true, then there is some system or a procedure of reimbursement that is being put in place. I don't know the specifics of that, but I know that this is one example where um, regulatory bodies definitely want to put not just regulatory bodies, but medical associations are trying to put in place some sort of process so that it's not like always up to the healthcare institution to determine how this goes, but it is happening at a case by case basis, mostly because AI tools in imaging have advanced significantly more than AI tools in other areas. And so it's very hard to come up with a universal way of saying you will always reimburse every time an AI detects something. And it's not true because not every model is validated for the exact purpose that it is being used for. And so there are definitely bigger regulatory concerns on that front. But that work is actually happening. Whether or not it will increase or decrease costs, it's a complicated question in the sense that if you did manage to show that using the model can lead to potential reliable early prediction, then you might be able to prevent certain adverse outcomes. And so the cost benefit trade-off by intervening early, but the cost benefit trade-off is like hard to assess for that one patient. It has to be done across multiple studies and large scale studies to show where exactly amortized costs are actually going down versus immediate costs might actually be going up because you're intervening more, but you're intervening early. So eventually the patient's healthcare utilization goes down and their outcome is better. So that will take some time. It's not very different from how drugs are trialed or some other intervention is trialed, except here the big difference is that AI models can be trained on specific kinds of data, and they might have to be retrained and updated depending on how things are changing within the hospital system or across hospitals.
Okay, Understood.
Okay.
Thank you.
AB, you had the questions, and you're raising your hand. Okay, I don't know. So maybe I have just one last question for you, Professor Joshi. How do you see the evolution between the foundation models, so the ones that the universities, Columbia, Stanford are doing, so they on the private ones like Google, Gemini Health, kind of models. So how are they going to coexist? Um, I assume that the private models have access to more compute, so maybe that the bigger the models are bigger, might be more performing, but they don't necessarily have access to the EHR data on the data in hospitals. So how should we see that dynamic?
Yeah. So that dynamic is actually interesting in that these models that are private, like Gemini built by big tech, definitely have a lot of context, say from publications and things like that. But so it'll be like having read all possible medical textbooks that are existing in the world. But if you put like a specific patient's trajectory of an entire decade, the model will not be very good at figuring out the outcomes. But if you look at the foundation models but the foundation model is built by the hospital is designed to basically create a patient summary, but doesn't have context of all the world's publications. So eventually, some combination of the two will lead to the most benefit. Right now, what's happening is that because of like many logistical concerns of data access and so on and so forth, these are separate entities, and so even if you use a chat GPT to put in, say, let's say I was allowed to put in patient data into a chat GPT, or the patient themselves did it and tried to get a diagnosis, they will get a diagnosis based on our scientific knowledge and medical knowledge, but not based on their own trajectory in the past. And so the personalization aspect is a little bit less over there, unless you are able to combine both of these aspects, and people are definitely trying that.
Okay, thank you. AB, yeah, please go ahead.
Yeah, hi. Just had a quick question. So I'm a physician myself, and I just wanted to find out how are you having access to the data with all the HIPAA compliance, which I think was the earlier question as well. But just to get an understanding, if we do not have access to a huge volume of actual clinical data for patients, how accurate would the predictability be, like for these kind of like spine patients or brain tumor patients or brain lesion patients? Like how do we determine if it's accurate or not?
Yeah, so I sit in the medical center and I work with basically we take the electronic health record data, it is de-identified, it is made into a form that is HIPAA compliant, and we train our models in-house. This is not something that the data that is CMC patient data that is put into a GPT. We train the GPT model on our lab servers. So which is a HIPAA compliant server, and I'm allowed to do that. So because of that, these models are basically in-house trained by these large medical centers because they have the capacity to do it. And so if you cannot actually put that level of data and compute resources into being able to train the model, their predictive capabilities will go down. That much is true, and that is kind of the result that I showed you. If you trained a very task-specific model with very limited data, they will be able to do some predictions, but they may not be very good. But if you can actually leverage patient trajectories and build the models correctly, there is strong potential to help clinician practice as well as by doing better predictions.
Okay, excellent. So we passed the time. I wanted to thank you very much on behalf of all the participants for your excellent presentation and all the work that you are doing. I think this is one of the most exciting area of application of AI in real life. I think AI and health and medicine. So I encourage you to visit Professor Joshi's webpage at Columbia to look at the work of her team on all her publication. I recently read a paper on explainability in AI on medicine. It's a very
Yeah.
interesting paper. What matters to explain results in AI on health. So thank you very much, everyone. Next talk will be I'll give a short talk on AI and consciousness. So it's more like esoteric, but it will be an interesting topic. Okay, so thank you all, and thank you, Professor
Thank you.
Joshi, again. Okay,
Thank
see
you.
you
Have a
again.
good day.
Okay, bye bye.
Bye.
Bye bye.